I direct the Southern California Particle Center at UCLA, and we've been in existence now going on 13 years. And so I'm going to just highlight some of this. We have probably 400 papers, and so that we have a lot. So that if there was ever a time to talk for an hour, or go into more detail, I'd be very happy to do it. So don't hesitate to ask if I can be of assistance in the future. So I'm going to talk about some of our research findings. I think that Phil Fine has told you about ultrafine, so I'm going to assume knowledge on the part of the audience. Basically, our particle center, our objective is to determine the basis for health effects from ambient particulate matter and vapors, and I'll emphasize vapors because it's not been given attention. Mobile sources has been our major foci. We've done railroad studies. We've done a study at LAX, which I'll mention. When we have, of course, dealt with diesel and with vehicles. We want to determine the chemical and physical properties. We want to link those chemical and physical properties with adverse health effects, and we've wanted to define the mechanistic features of illness and disease from air pollution. Next slide. Now I just want to point out I don't know what Phil did, but I want to point out some interesting features. I'm going to come back to this later. Notice let's assume this is a diesel particle, an ultrafine diesel particle. And what you see is the soot core, which everybody's familiar with. But you should also notice the adsorbed toxics, which are in the green around the soot core, and look at the condensed phase toxics, that is semi-volatile materials that condense from being hot and becoming cooler. Deepest region of the lung. And next slide. And they cause alveolar inflammation. That alveolar inflammation produces immunologic responses. Those immunologic responses then move to the heart, move to other parts of the lung, move to the brain, move around the body, and cause alveolar inflammation. Alveolar inflammation's partially responsible, if not wholly responsible, for heart attacks, responsible for asthma, and so on and so forth. So you can see the brain uptake, you can see the deep part of the lung uptake, and gives you a sense of why these particles are toxic, because if they're entering cells all the way through the lungs, they are then going to produce immunologic responses that cause inflammatory processes. Next slide. Now, this is, if you take an animal, a mouse, and you treat them with a protein called OVA, what they do is that sensitizes the animal so that the animal becomes allergic. But if you then take the OVA and ultrafine particles, look what's happening on the top slide. I've been talking about inflammation, and I don't think I have to push the point, but look at the level of inflammation in those lungs. You have mucose substances in the second that are formed. Those are polysaccharides. Those are big, long sugars. And in the bottom, you have white blood cells that have been formed. So what happens is, if you think of a child who's sensitive to asthma, and so that they are in the category of people who have been exposed to the OVA, if this makes sense to you, if you take sensitized, susceptible people, and then you add ultrafine particles, you are going to catalytically increase the impact, and therefore this is a slide which we think emphasizes the potential for asthma. Next slide. So ultrafine particles are capable to enhance the primary allergic sensitization response to experimental allergens, and inhalation of real-life ultrafine particles leads to profound allergic inflammation deep in the lung in the previously sensitized animals. So this shows you the connection between susceptibility on the one hand and disease production on the other. All right, here's a mouse study we did with the ApoE mouse, and I won't go into the details. We gave them non-exposed air, we gave them filtered air, we gave them fine particles at PM 2.5, and we gave them ultrafine particles. Next slide. And if you look at these slides, look at the ones with the ultrafine particles. Look at these are aortic lesions. These are inflammatory lesions in the aorta, and there's a dramatic difference between the fine particles and the ultrafine particles, and there's a vast difference with the filtered air. So that when you actually quantitate this, next slide, keep going, you can see that the ultrafine particles lead to the most massive, the most massive aortic lesions, and there are fewer with the rest. And so that's an example of ultrafine relationship to heart attacks. We've looked at the issue of what we call oxidation of low-density cholesterol, the bad cholesterol, and that occurs, and that's part of the atherosclerotic, the heart disease, cardiovascular problem. But these are real results in animals that the aortic lesions were highly sensitive to the ultrafine particles. So we have also seen changes in humans and senior citizens with respect to blood pressure. We've seen a restriction or thinning of the blood supply. And again, we see airway inflammation produces immunologic responses and the exacerbation of atherosclerosis. And I'm assuming everybody knows atherosclerosis. If not, we'll just call it cardiovascular disease. Now, I'm changing subjects. Here's elemental carbon, which is a surrogate for diesel. And let me just say, this is not a talk about freeways, but I'm going to just use it for a second, because elemental carbon is a surrogate for diesel, and diesel contains 90% ultrafine particles. Wow. Make no mistake about it. What you're seeing here is 12 cities throughout the South Coast Basin, and what you see is that as the elemental carbon goes up, the amount of air that one can breathe out goes down. And so the percent of people with FEV1 less than 80% goes up. So that what you're seeing is on the far right side is people whose lung function is impaired. And that's a diesel exhaust response, but again, what we see with diesel is the same thing in terms of the particle size. In fact, the aircraft particle size is even smaller. Next slide. Now I want to mention, these are kids that we were studying, and if you look at the kids who've had reduced lung development, they have reduced lung development because of their exposure to particles and vapors, and that if you see that the kids who've been exposed to particles and vapors, their lungs haven't grown. And the point I want to make here is that puts them at risk of cardiovascular disease and respiratory disease and mortality throughout their lifetimes. This is not just a children's disorder, although it's a major disorder, as you well know. But the point I want to make is that this is a lifetime effect. If your lungs don't grow by the time you're 20, you're going to have the consequences of a reduced lung function throughout your lifespan. Now this is just a simple slide. This shows that the closer you get to freeways, the more you have odds rate, increased asthma. And my point here is again, we're talking about ultrafine particles, we're talking about diesel, and we're talking about chemicals that are not dissimilar from what we see at Santa Monica Airport with the jet aircraft. So we have to speculate that we see neurodegenerative diseases, which I've already mentioned. The labeled ultrafines are translocated from the lung to the brain. The important thing is that the brains of the mice that we exposed have increased markers of inflammation, but it's chronic. It's chronic. We see the inflammation 2 weeks after the last PM exposure. So if you think about breathing ultrafines throughout your lifespan, you're going to have chronic inflammation, it's not an acute response, it's a chronic response, and that may have implications for Alzheimer's, for Parkinson's, and for other disease states. Next slide. And this is just oh, that slide didn't turn out so well, but basically, without getting into detail, we see relationships with traffic, and you see evidence of preterm and low-term birth weight babies. And so the ultrafine particles from traffic or aircraft, perhaps, are significant in terms of having developmental effects as well as the other things that I've talked to you about. You see, the point I want to make is everybody talks about how over the last 10 years, 20 years, 30 years, the air's gotten better. Well, it hasn't. What's happened is we have discovered heart disease, asthma, developmental effects, atherosclerosis. Yes, the air has gotten cleaner in terms of visibility, but the diseases that we now understand are responsible from those exposures we didn't know about 10 years ago. And so all of a sudden you can say, yes, the visibility is not backyard barbecue pits, and that goes without saying. It's what we have seen is new diseases, and we haven't seen the end of this process. And I'm not going to talk about cancer, but there is no question whatsoever, I don't care who says it, there's no question whatsoever that diesel exhaust causes lung cancer in humans. There are 50 studies. These epidemiologists debate and debate and debate and debate till your head comes off. But the fact of the matter is there's no data set like the 50 studies that show positive cancer effects as well, and I don't have time for that. So what we've shown is effects on the central nervous system and the autonomic nervous system. We've shown low birth weight in preterm babies. We've shown an increase in asthma and other respiratory diseases. We've seen a decrease in lung development and function in children. We've seen atherosclerosis, and we see oxidative stress, which means exposure to what we call pro-oxidants and electrophiles. Those are types of chemicals, and those come from what you saw what I stressed with the slides on the epithelial cells and the mitochondria, that you have these mechanisms that we now understand. And so what we've done in our lab is we can now predict from the time you're exposed until the time you become diseased, we can tell you what the entire process looks like in that what we'll call a roadmap. So that's it for me. I hope this is informative. Thank you.
Thank you. Thank you for that presentation. Earlier, Dr. Fine informed us that ultrafine particles were not regulated. And based on your research, do you believe they should be regulated?
Well, the answer is yes and no. And Phil knows I feel this way, so he won't hit me across the table. What I feel has to be regulated, I showed you the soot core. I showed you all the chemicals that are on the soot core, and I've showed you the vapors. We find, by the way, major toxicity associated with vapors, and nobody has studied vapors for the last 100, they've never been studied. We're the only lab in the United States, except maybe for Lovelace, that is studying vapor phase chemicals. So to get back to your question, what I think has to happen is here's your ultrafine particle. It's in the epithelial cell. It's in the mitochondria. As I said before, what's happening is those organic chemicals that are on that surface and those metals are coming off and exerting their toxicity. The soot core isn't toxic. So what the ultrafine is a vehicle for bringing organic chemicals and metals to sensitive parts of the body and to the lungs and what have you. So my sense is that, yes, we can do another PM 2.5, which is not adequate, as we know, and we can do a better job with ultrafines. But we have to regulate those organics and those metals. And that's because they're the ones that are etiologically directly connected to toxicity. They're the toxins. The soots aren't the toxins. So the ultrafine gets you there. It gets it to your brain. But it's the other chemicals that cause the disease.
Thank you. Bill, do you have any questions?
Just curious about the relationship to the Santa Monica Airport. Do you see that as an issue?
I completely do. Most of you know Ping Ho. Ping Ho's son in the 8th grade and I did a study of the Santa Monica Airport. And I think Ping, if she's here, we could probably make that available. It was a great study. We should have published the damn thing. We didn't. He's an 8th grader. You know, they don't think in terms of academics who want to publish or perish. And we showed in that study that there are significant ultrafine particles in the Santa Monica Airport. So my showing you LAX wasn't entirely off base in that sense. So yes, I think that that the kind of study where we looked at the particle distribution that I showed you, that would be a very useful study. But let me tell you something, if I may. I don't mean to be so assertive.
It's okay.
What we have 10 or 11 assays we do at UCLA that measure the toxicity and the pathway that I talked about. What you want is to use some of those assays to not just measure the amount of the emissions, but we have quantitative measures that measure the level of toxicity of those constituents. And if you can measure the toxicity of the constituents, then you have something to hold onto your hat with and regulate and make policy decisions.
Do you think if there was a bigger buffer from that airport to the citizenry, that would dramatically decrease it? And should there be, what would be your solution? Forget politics. You don't have to play politics. Just straight out how you see this. What could we do?
Well, let me just say this. I didn't show you a number of slides, but we see that it's not just at the blast fence at LAX, but if you go downwind all the way to the 405, we still see the particles from the takeoff. So you've got a distance to characterize. And the second thing that we saw is we went to the other side of the 405 and went far away from it so we weren't impacted by the 405. And what we did was we looked in people's backyards who were far, far away, and we found particles like we're talking about from planes coming in to land. So you've got takeoff and you've got landing, and the particles from takeoff go a very long distance. So the fact of the matter is, what that means is one has to do studies to look and see how far the community is being affected by the jet stream going back, because there are millions upon millions of particles that are probably reaching homes.
Thank you.
Thank you.
Have you had any conversations with fuel experts as to whether one fuel or another has a significant effect, and what kind of combustion is involved in complete combustion? What would the ideal fuel be?
Yeah, the question that he's asking, that Channel 35 will be able to record, because that's why I'm saying it, is how impactful is it? Could you change different fuels? How could you make it better, is basically what he's saying about the exhaust.
I'll tell you what we did. This was a small study, and what we did was we didn't look at fuels. We should have. My fault. We didn't have enough money. What we did do, though, is look at the differences between jet aircraft engines and emissions. And there we have data that suggests that there are differences between jet aircraft engines. So the question you're asking and the question the way I just answered it are part of a package, I think, that deserves further investigation.
Thank you, Doctor.
Thank you. I really appreciate it.